In the last video, I laid out the game plan for Chapter 3, and that was to consider the 95% confidence interval and do that by first thinking about a situation where we're getting a 95% confidence interval on the population mean when the standard deviation of the population is known. Follow that by 95% confidence interval on the difference between two population means when the standard deviation is known. Follow that by 95% confidence interval on a single mean when sigma is unknown. And finally, what we're really interested in is 95% confidence interval on the difference between two population means when the population standard deviations are unknown. And so this video is going to focus on section section 2 of this chapter, and it's going to be on the theory that underlies calculating a 95% confidence interval on the mean when the population standard deviation is known. So what we have here is a figure from your notes with these 4 different panels that I'm going to go over. And we're going to start with the first one. And the whole idea in these panels is that we're going to deal with IQ. And we know IQ is normally distributed with mean equal 100 and standard deviation equal to 15. So, if that's the case, what I've got here is Y. So what I have on the x-axis that I've identified as Y is the IQ of each individual. What we have on the y-axis is the probability density function associated with each one of these possible IQ values. Remember what a probability density function is. It's a function, so it's just a meat grinder. And what goes into the meat grinder is going to be a possible IQ. And what comes out of the meat grinder is the probability density function associated with that particular IQ. We have a cat in the room, so just bear with me. There we go. Four, three, two, one. So having disposed of the cat, we have on the x-axis the IQ, on this axis the probability density function of the IQ. We know that IQ is normally distributed with mean 100 and standard deviation 15. And so we can express this as Y, the random variable Y, the set of all possible values of lowercase y is normally distributed with mean 100 and standard deviation 15. Now what we're going to do in panel B is we're going to take samples. Samples of size 9. We're going to calculate y bar, the sample mean. So now what we've got is a probability density function. On the x-axis, we've got y bar. On the y-axis, we've got the probability density function of y bar. So again, it's not that different from what we saw before, except now what goes into our meat grinder is y bar, and what comes out is the probability density function of y bar. So what can we say about this curve? What we can say about this curve is that if the set of all possible values of y, the random variable capital Y, has this distribution, then we can say that the set of all possible values of lowercase y bar would be the random variable capital Y bar, and it's going to be normally distributed. It's going to have the same mean as the underlying population, 100, but its standard deviation is going to be reduced. Standard deviation is going to be sigma divided by square root n, and in this case That means it's going to be normally distributed with mean 15 divided by the square root of 9. In other words, normally distributed with mean of 100 and standard deviation equal to 5. And these vertical lines here are meant to represent the standard deviation. So in the first instance, we've got a standard deviation of 15 in the underlying population. But when we take sample means and look at their variability, they're going to tend to be less variable because the high IQ and the low IQ are going to tend to average out, and therefore you get a smaller standard deviation. What we see in this figure is that if we apply our rules of variance, if we start off with the average and then we subtract the constant from it, and that constant is the underlying population mean, then what we're going to have is a normal distribution, the set of all possible values of y bar, which is capital Y bar, minus mu, is going to be normally distributed with mean 0 and standard deviation 5, because you know what subtracting that constant is going to do. Subtracting the constant is going to change the mean from 100 to 0, but it's not going to have any effect on the standard deviation, so that remains at 5. And then finally, in our last step, what we're going to do is we're going to divide by sigma divided by root n. So now if we consider all possible values of y bar minus mu over sigma root n, in other words, our random variable, capital Y bar minus mu over sigma over root n, what that's going to give us is our standard normal distribution. And we've really seen all this before. It's just a reminder that if we have this random variable, y bar minus mu divided by sigma root n, that you're going to have a standard normal distribution. And the standard normal distribution is important because that's what we're going to use to enable us to use the Z table, the standard normal table. So here we have our standard normal table. And remember what our goal is. Our goal is to calculate a 95% confidence interval on the mean. So a 95% confidence interval. So that means there's a 95% probability that our interval is going to straddle the mean. Which means there's a 5% probability that the interval does not straddle the mean. And we use a sigma alpha to represent this probability. The probability that the interval doesn't straddle the mean. So we're going to say that alpha is going to be equal to 0.05. That's the probability that the interval we construct doesn't straddle the mean. So now what we're going to do is we're going to use a t-table. And before we use a t-table, we're going to do a little bit more algebra here. We've got alpha is equal to 0.05. We're going to calculate 1 minus alpha over 2, which is going to be equal to 1 minus 0.05 divided by 2, which is equal to 1 minus 0.025, which is equal to 0.975. And that's the number we're going to look for in our t-table. So we're going to look for our t-table and look for a value of 0.975. And where are we going to find that? We're going to find that right here. So there's a value of 0.975. And we go to our margins. The first two decimal places, first two significant digits are the 1.9 come up here, we get an additional 0.6. So the Z value associated with the 0.975 is 1.96. Let's come up here and look at this graph here and think of, well, what does this 0.975 and this 1.96 mean? What it means is 1.96. That'd be right about there. Right about there, 1.96. And what that implies is that 0.025 would be the probability of having a Z value less than or equal to 0.975. So that's what that means. But recall that the Z distribution is symmetrical. So if we came out here to minus 1.96, minus 9.6, that would put 0.025 in here. So we got 0.025 at both the ends. So what does that leave? That leaves 0.95 in the middle. And that's really what's important because it's a 95% confidence interval that we're interested in calculating. So let's put the ideas of the last two slides together. Remember, we said that y bar minus mu of sigma divided by root n has a standard normal distribution. What we have here is the standard normal. And remember, this is a random variable. It's the set of all possible values of lowercase y minus mu over sigma divided by root n. So that's what we've got here. So what we can say is, we just showed that if we had a Z value of 1.96 and another Z value of minus 1.96, if we considered all possible values, we did the experiment an infinite number of times, and each time we calculate a different value of lowercase y bar, 95% of this, and again, this would correspond to the random variable, capital Y bar, 95% of those values are going to lie within minus 1.96 and plus 1.96. And so just as a reminder, this is what we did on our Z table. We were interested in a 95% confidence interval, so we calculated 1 minus alpha over 2, and that enabled us to get that Z value of 1.96. So now what we're going to do is a little bit of algebra. So the takeaway from the last slide is that the probability of the random variable y bar minus mu over sigma divided by the square root of n, the probability of that value, random variable, lying between minus 1.96 and positive 1.96, that probability was equal to 0.95. And that's what this line here shows. So we've got, there's our y bar minus mu over sigma root n greater than minus 1.96 less than 1.96. Now, find point, is it less than or equal to, or is it less than? Well, since we're dealing with a continuous variable, it doesn't really matter which we use. I'll use either one. I don't think it makes any big difference. So, this line here represents this truth here. And now we're going to go through a bunch of algebra. And the first thing we're going to do is multiply. We're going to multiply all three of these components by sigma root n. So that means we're going to be left with y bar minus u here, minus 1.96 times sigma divided by root n, 1.96 times sigma divided by root n. Now what we're going to do is subtract y bar from all three components. So we're going to subtract y bar, so you get minus y bar there, and minus y bar there. And this next step, we're going to multiply all three components by the number minus 1. And what that's going to do is it's going to flip these inequality signs. Now, that may seem a bit strange, so maybe I'll just go over a quick example. Consider the following three numbers. Minus 7, which is less than minus 3, which is less than 4. Now, let's multiply everything by minus 1. What do we get? We get 7, we get 3, and we get minus 4. Now, in order to make that work, what we have to do is flip the inequality signs, so now we've got a true statement. So that's what's happening here. Everything is multiplied by minus 1, and as a consequence, we've flipped the inequality signs. And now in this last step, what I'm going to do is I'm going to take this component and move it over here. I'm going to take this component and I'm going to move it over here. So again, I'm going to have to reverse the inequality signs. So that would be equivalent to saying, once again, that minus 4 would be less than 3 would be less than 7. So that's effectively what I've done here. So this is where we want to be, because this is our 95% confidence interval. This is the upper limit. Excuse me, this is the lower limit. And this is the upper limit of a 95% confidence interval. And what we can say, therefore, is that probability that this particular value, y bar plus or minus 1.96 times sigma over root n, straddles mu is equal to 0.95. And actually, I think I made a bit of a mistake here. And instead of erasing it, I think I'll just go over it as kind of a learning thing. It would have been better to have done that. To have used capital L and capital U, excuse me, because what we're dealing with is y bar. We're dealing with the random variable. We're dealing with the set of all possible values of y bar plus or minus 1.96 times sigma over root n, which we could have gotten had we repeated the experiment an infinite number of times. So we'll stop there before moving on to the next subsection.